Hi, and welcome to another episode in our BQIT lecture series. Today we'll be talking about quantum key distribution and the Bell inequality. Now, quantum key distribution is a method of securely distributing keys for use in encrypting messages between two parties. So let's say that we have two parties, Alice and Bob, that want to send messages to each other. So normally it's Alice who wants to send Bob the message. And let's assume that we have Charlie, a third participant, who, and we have Eve, which is a shorthand for eavesdropper, who wants to intercept the message that's sent from Alice to Bob. Now, of course, Alice does not want Eve to know the contents of the message to Bob. So the main problem of cryptography is how to send a message securely such that only Bob can read the message and not Eve. So one approach to this problem is called symmetric key cryptography, which means that we use the same cryptographic keys for both encryption and decryption. So a key is basically information that is used to encode a message or decode it or encrypt or decrypt it. So in the case of symmetric key cryptography, the same key is used to encrypt the message before it is sent by Alice to Bob. And the same key is also used by Bob to decrypt the message sent by Alice. And of course, if the eavesdropper does not have access to this key, Eve will not be able to decipher the message sent from Alice to Bob. Now, another approach is called public key cryptography or asymmetric key cryptography, which uses different cryptographic keys for the encryption of the message and the decryption. So normally the key that is used for the encryption is called the public key, and the key that is used by Bob for the decryption is called the private key. Now, both approaches have their pros and cons. So the advantages of symmetric key cryptography is that it is fast and quick, and it's suitable for encrypting large volumes of data. But on the other hand, key distribution and key management are quite difficult. So keys must be changed periodically because if Eve somehow manages to get their hands on one key, on either key, then Eve can easily decrypt messages or even send false encrypted messages to Bob. So this means that something called key distribution, which is basically distributing keys to the relevant parties and withholding access to malicious parties, is important. So in a classical case, there are several obvious approaches to classical key distribution. The first is meeting face to face, Alice literally giving the key to Bob. Another could be through a key distribution center. So Alice could use as a key distribution center to indirectly transfer a key to Bob. Or another approach could be sending the key through an existing encryption channel, basically sending the key by encrypting it using a previous key. Now, of course, some of these approaches are impractical, sometimes unsafe, and sending a key through an existing encryption channel requires that that channel is already secure. Now, of course, in quantum information, there is also a way to do key distribution, which we call quantum key distribution, which basically means distributing keys that are used for encrypting quantum information. Now, the thing with quantum information is that it can take advantages of these three properties: no cloning theorem, superposition, and measurement in quantum mechanics to securely encrypt messages and protect them from malicious attackers such as Eve. So if so first, no cloning theorem for reference states that it is impossible to create an independent and identical copy of an arbitrary unknown quantum state using some unitary operation. So it can be proved by the following procedure. Let's suppose that some unitary evolution affects the copying procedure. Basically, let's say there does exist a procedure for copying a state psi onto some blank state we're just going to call S. And the outcome we expect to be psi cross with psi. Now let's suppose this procedure works for two different states, pure states, psi and phi. Then we have these two different states at the end of the procedure. And if we take the inner product of these two states, we get this result. But of course, since we've assumed the operation is unitary, the left-hand side, this matrix should be I, leaving us with this expression on the left-hand side and this expression on the right-hand side, which leaves this expression implying that the inner product of psi or phi is either 0 or 1. So basically, such a unitary operator only exists in the case of two states that are orthogonal or equal to each other. So basically, a cloning device can only clone states that are orthogonal to each other or already basis states. So in general, such a quantum cloning device doesn't exist, and this no cloning theorem can be used to basically protect eavesdroppers from copying intercepted messages without the knowledge of both parties. Now, such quantum properties are used to develop many different protocols for key distribution. And one of the simplest protocols is called the BB84 protocol, which we're going to look at right now. So the BB84 protocol basically uses two different bases to encode 2 bits, 0 or 1. So let's say we have two different bases, the horizontal and vertical bases, and the diagonal and the anti-diagonal bases, defined as follows. So let's suppose Alice wants to encode a bit. Alice first chooses a basis to encode, and then it chooses the bit she wants to encode. So if she wanted to send this bit 0 to Bob, and she chose the horizontal vertical basis, she would represent it as this vector, the horizontal vector. And if she chose the diagonal on the anti-diagonal basis, she would have chosen this vector instead, and vice versa for the 1 bit. Now, in Bob's case, what Bob does is he chooses randomly a basis to measure the state sent by Alice to him. So he picks either the horizontal vertical basis or diagonal anti-diagonal basis, and he makes a measurement of the final vector sent by Alice. Now, for example, let's say Alice encoded this state, the bit 0, using the horizontal state, and Bob measures it in the horizontal and vertical. He would have measured the 0, he would have measured this state with 100% probability. If he instead chooses this basis, he would either measure this state or this state with equal probability, and so on for these different examples. So let's say in the first stage, Alice sends messages to Bob using this procedure. And so in the first stage of the secret key, she sends this message, of course. And then what Alice and Bob do is that they compare the answers they get later on and only keep the bits that are measured by Bob in the correct basis. So for example, let's say that Alice sends Bob a one bit that in the diagonal and the anti-diagonal basis, but Bob measures it in the horizontal and vertical basis, and Bob gets a value of 0. Well, after the fact, Alice and Bob will communicate, and since Bob measures it in a different basis, they would both agree to just get rid of that measurement altogether. So, for example, in this measurement, these would be the bits that are kept by Alice and Bob in the first stage. So we get this first stage secret key sent from Alice to Bob to be 00000111. And in this, okay. So next stage, let's say that there's this malicious attacker Eve who wants to access the information sent from Alice to Bob. And so let's say Eve intercepted the information from Alice, and he measures a state sent by Alice in the anti-diagonal diagonal basis. And we get this diagonal state instead. And then he sends the state along to Bob as if nothing has happened. So Bob gets this diagonal state. And then Bob measures it and gets a horizontal result, which actually somehow matches the original bit sent by Alice. But sometimes he might get the vertical basis, no, not the vertical vector. And this would be different. This would be incorrect. So in that case, then Bob would sometimes find indiscrepancies between the measured data and the actual data sent by Alice. So if an Eve exists, then this would actually be detectable in the amount of discarded bits after post-selection. So in the full process of the BB84 protocol, Alice chooses a basis and a bit string, and Bob also chooses a basis for each bit. And Bob starts measuring, and they compare the bases only. And then this leads to the generation of the first stage secret key. Now they repeat the same process using the bases they both agreed upon. And they use this to detect eavesdropping and to generate the second stage secret key. They then perform error correction in the case of bit flip errors. And they also do something that's called privacy amplification, which is basically a procedure used in classical cryptography to reduce the correlations between the information between Alice and Bob that could be used by a malicious attacker. Okay, so let's move on to another topic in quantum mechanics called the EPR paradox and the Bell inequality. So this experiment basically is fundamentally aims to answer the question of what exactly is the difference between quantum mechanics and the classical world. So the EPR paradox aimed to disprove quantum mechanics once and for all, and to prove that classical realism was the correct way of looking at the natural world. So the EPR paradox was suggested by Einstein, postulated by Einstein, Podolsky, and Rosen. And it basically stipulated that if, without in any way disturbing a system, we can predict with certainty the value of physical quantity, then they should be an element of reality corresponding to that quantity. Basically, it states that every single measurement should be predictable and deterministic, and any probabilistic theory, such as quantum mechanics, can be explained by a rivaling classical theory with something called hidden variables. So this was grounded into philosophy of basic the realism and instrumentalism, which states that the only real facts are that can be proven empirically and through measurement via scientific instruments. So Einstein's realism is what's called actually local realism, which means that physical interactions are transmitted at finite speeds. Basically, we cannot have non-lo we cannot have global phenomena, i.e. spooky action at distance, that in which information is transmitted instantly. And so it denies the possibility of correlated effects that happen faster than the speed of light. It is also grounded in the philosophy of realism, which states that the observable physical properties of a physical object are inherently given to the object regardless of measurement of experience, which is in direct contradiction of quantum mechanics, which states that the properties of a quantum state, of a quantum system, are not determined prior to measurement, but instead the the properties are manifested at the time of measurement, and that the state is uncertain. Instead, all of the different outcomes exist simultaneously in a superposition. So it rejects the Copenhagen interpretation completely. And Einstein's basically is in favor of hidden variable theory, that if the outcome is deemed to be probabilistic, it's not due to quantum mechanics, but due to some hidden variables we haven't accounted for. So Bell's inequality actually aims to resolve this conflict between Einstein's classical hidden variable theory and the probabilistic theory of quantum mechanics. So Bell's inequality is basically a test of the local hidden variable theory. If the local hidden variable theory is correct, then the Bell inequality should hold. And if it is violated, as we will see is indeed the case later on, quantum mechanics is further supported since hidden variable theory is ruled out. So Bell's inequality performs what is called CHSH measurements, in which, let's suppose we have this third party, Charlie, that generates two particles of different states and gives each one to Alice and Bob. And so Alice has two different outcomes, well, different bases it can measure the particle in. And particle 2 can also be measured in the same way, and each of these outcomes are labeled according to these letters Q, R, S, T. So Q and S are on this one basis and R and T on another basis. And so Bell's inequality is basically that if hidden variable theory is correct, then this quantity S defined by this should be less or equal to 2. And so let's suppose that we have hidden variables, which basically states that the outcomes, the measurements by Alice and Bob, must be independent with each other. So let's suppose that if, for this case, then Alice measures R to be -1, T to be 1, and of course RS would be -1, R2 would be -1, QT would be 1, and so on and so on. So R would be minus 1, S plus 1, Q plus 1, T minus 1, and we can multiply these products to get these results right here. So now we can calculate these expectation values using this expression here, and these expressions can be calculated in the same way. And so S can be represented as this, with P being the probability of a certain value of QRST. Now, if you look at this expression here, we can do some algebra and factorize it. And you notice that there are only two possible outcomes, 2 or negative 2. So either this is 2 or negative 2, which means that this quantity needs to be greater than the negative 2 case and less than the all 2 case over here, which basically is the inequality we stated over here. So let's see what the outcome is for quantum theory. So in quantum theory, instead of two different independent particles, Charlie generates this entangled state, particles A and B. So if Alice measures an outcome of 1 here, Bob will measure an outcome of -1 in the opposite for the opposite particle and vice versa. So let's say that the two bases are basically Q and R is the Z basis, R is the X basis, S is the minus Z, this basis, and T is this basis. So according to quantum theory, if you calculate everything, S should be 2 to the square root of 2. So let's say, for example, that we want to calculate the expectation value of QS. Then according to the definition of QS, of course, then we get this value over here. And then doing the algebra, we get this expression here, and then we can calculate this over here. And then we get a value of square root 1 over square root of 2, and this can be repeated for each of these entries of 2 to square root of 2. So which is correct? Well, it turns out that S, when measured, S is actually found to be 2 to the square root of 2, of course greater than 2 in violation of the CHSH, which means that quantum theory is correct. And this actually experimental implementation was actually awarded the Nobel Prize. So it has actually been experimentally verified that Bell's inequality is violated and that quantum theory gives the correct value of S, not classical hidden variable theory. So we can rest easy tonight knowing that quantum theory is correct. But that's all for this lecture. I'll see you in the next lab.